Welcome to Lecture 2 of Computer Science 181. Today we'll be continuing to talk about regression. And I wanted to start by actually showing you just a few examples of regression problems, just to set the way that we can think about what this is all about. So let's remind ourselves, first of all, that we're talking about supervised learning at the moment. So supervised learning is a setting where you're given not only X, which will be our features, but you're also given a target label in your training data. So your data is X and Y, and you're trying to predict a label Y. And in particular, we're talking about regression problems. Regression problems in one dimension are a one-dimensional X. We're always going to be, almost always, we'll just be thinking about a one-dimensional prediction problem. So Y will typically be one-dimensional in this course. And to coordinate you on the cube, what are we doing? We're doing supervised learning. We're thinking about continuous problems, and we're thinking non-probabilistically. And if you're not even sure what it means to be thinking non-probabilistically versus probabilistically, that will become less mysterious on Tuesday of next week, when we'll be talking about probabilistic approaches. All right, so what is linear regression all about? Well, let me give you a few examples. One is this airline problem. Airlines need very badly to be able to predict when a flight will arrive late. Now, you probably don't even barely remember what an airplane is these days, but this story from Bloomberg from 2013 says that even a very small prediction, error in the prediction of whether or not the flight will be late arriving at the gate, can have a lot of knock-on effects that can be extremely costly. And you can imagine that this regression problem, this problem of predicting the time at which a flight will arrive at the gate, is very complex, because it doesn't just depend on things on the ground, it depends on the weather systems as well. Here's another example. This is from Netflix. Obviously, we're all increasingly consuming personalized content, and you can think about the rating prediction problem as a regression problem. Think about trying to predict a number between let's say 1 and 5. Think about it as a continuous number, maybe 4.7, meaning we predict you will really like it, and using that predicted rating to try to decide how to rank content that you might be interested in watching at Netflix. And there have been studies, for example, by Netflix that have shown that by using recommender system technology, they can dramatically reduce the churn on their customer base. And reducing churn, reducing the rate at which they lose customers, saves them a lot of money because they don't have to work as hard to gain new customers. Okay, so it's this kind of alignment between trying to make the users of the platform happy, meaning they stick on the platform. Another example, this one's like completely different. Imagine this massive machine that's crushing concrete. It's actually pretty hard to imagine, but look at this. This is huge, very, very powerful machine. And it's important for civil engineering to understand what is the compressive strength of concrete. And you can imagine trying to build predictive models to try to predict at what point will this particular piece of concrete break, using features like the amount of water, or what is the aggregate type that was used in making the concrete. Last example, I think, is Uber. Again, not sure about you, but I haven't tended to be using Uber as much recently, but this is a screenshot. There are not very many screenshots that actually show the vehicles in the Uber system. So if you squint at this, you can actually see all of the vehicles at a particular point in time that Uber was monitoring and dispatching. And obviously, Uber and companies like Uber would really like to predict supply and demand. They would really like to predict where origins of trips might be and when. because they may like to try to activate more supply of drivers, or they might like to try to adjust the pricing in the system to try to promote drivers to move to where there will be a lot of demand. And this is now not quite up to date, but typically will be building predictive models that will be predicting intensity of demand for regions in space. And if you want to read more about this, there's actually a fascinating technical paper that talks about the ability to use hexagons to tessellate the entire world. There's some kind of a tessellation theory that is supportive of why hexagons are good shapes, which I just think is curious. So that's like, you know, a little bit about motivating settings. I want to bring Finale into the conversation now. Yeah. You must think about regression a lot, Finale, in your work. And just wondered if you could share with us some of the things that you think about.
There's something very useful about all of those examples that you just shared, David, in the sense that in all of those cases, there was already a problem that was set up. You know, the airlines needed to manage their logistics, and there was if you've taken 182 or some other kind of optimization, operations research sort of class, you know that there's constraint propagation and ways to, if you knew how late the airlines were going to be, you could solve the optimization problem of the routing. For Uber, the same thing. If you knew what the supply was going to be, if you knew what the demand, and the superpower that machine learning is providing in all of these cases is in a way identical, right? It's saying that if we knew these numbers, we could optimize our sales, we could optimize our pieces. And in my work, it tends to be similar, because if we knew, you know, how a patient's blood pressure would react to a particular treatment, then we would just have a decision-making problem and we would solve the decision-making problem, but we don't. So then there's a mini regression problem inside, or not a mini regression problem, a quite hard regression problem to figure out, you know, what is going to be the treatment effect of a particular drug.
Yeah, the other thing I really like about that is it gets to these choices you have when you're thinking about how to build learning systems. You know, should you build them in a modular way, which I think you're emphasizing here, where if you're American Airlines, notice that American Airlines was not building an end-to-end predictive model to try to predict how they should adjust the decisions that they're making about the follow-on schedule during the day. What they were doing was they were building a model that was able to predict the arrival time for any particular flight. And then, as you're saying, feeding that into a decision theoretic or optimization-based module that then is trying to make decisions.
And I think in the real world, that's often the thing that you want to do. I mean, in the research world, in my research, we were trying to do these end-to-end models in cases where the amount of data is quite limited. But then you have increased questions about transparency. Here you can check to see the quality of your regression model, and you feed it into your decision-making model or decision-making agent. You kind of understand what each piece is doing, and you can address your risks appropriately.
Exactly. Awesome. Also, I just wanted to quickly mention that I've been actually recently thinking about problems that companies like Nielsen have, where you may know Nielsen is a company that actually has a audience that they monitor to figure out what content they're watching, both on what they call linear TV, which is traditional television, and on video on demand kinds of platforms, and are very interested in building predictive models to try to predict how many people will watch a show. And that's a regression problem, right? And it's a very interesting problem because there are competition effects. You can think about that the features that you need to make available to the regression model reflect the other choices that consumers have. Right. And so I want to mention that because it's this nice economic aspect to it as well.
For sure.
Yeah. All right. Awesome. Thanks, Finale. So I'm going to now jump in and start sharing some notes. And I actually wanted to just very quickly start by reminding you of the question that we got to at the end of last class. Remember we were doing kernel methods, and we had this question that we asked you where maybe think about it like this. Here is a cloud of points. Notice they're pretty tightly clustered, but there's one point up here that has a higher y. And then here is the x that we want to make a prediction for. Remember we were talking about this kernel function? And if x is just a scalar, then the kernel function we were describing becomes very simple. It's just this, it's just e to the square of the difference between this point and all the other points. So you're taking this kind of weighted average. And we asked you to think about if you used this non-parametric kernel regression approach in this example, what would happen? Does anybody want to suggest what would happen? And I want you to imagine that this x is like all the way off to the right. Think about it being a long way from the other points. Go ahead and raise your hands if you have a thought about what might happen here. Yeah, Al, go ahead.
The output should be the average of the y values.
Yeah, you might think that, right? And indeed, that's technically correct in the sense that the output would be the weighted average of the y values. That's right. But in this case, there's a particular interpretation of what we would expect the kernel method to be paying attention to. Matt?
I was just thinking that it would just take on the value of the rightmost point because all other values would be further away. So then it gets like weighted down significantly enough that they're no longer valuable.
That's right. That's right. So because this distance is so far and because we have the squared distance in the exponent, then it puts all of the weights on the point that just happens to be the closest. And so you can see how you don't get a very good prediction if this point happens to be an outlier. Okay, so hopefully that gives you a little bit of intuition for ways in which these kernelized methods may begin to break. Thank you. All right, so what are we doing today? What we're doing today is we're going to be talking about parametric linear regression. And I want to start by just reminding us all of some basic things. So we're going to be talking about data, where the data will be a collection of x's and y's, 1 through capital N. And I'm going to try to underline vectors. So this y is a scalar. This example is a vector. It's a feature vector. And I'm also going to try to write this D as kind of a calligraphic D to represent data, because we're going to use capital D to represent the dimension of the feature space. So the example lives in a D-dimensional feature space. Just a note that we'll sometimes be using little I to index an example, and we'll sometimes be using little n. So don't be confused. You'll see n and I, little n, little I, to index an example. Okay, how to think about this? Generally, we'll always be working with column vectors. So here's my column vector for example I with the features 1 through D. These are real features. These are the reals. So it's a D by 1 vector, feature vector. Now, what else do we have? We have our target of the regression problem. It's just a real. Y sub I is just a scalar. And the goal is that if I get a new X example, then I want to try to predict a Y, which we'll call Y hat. So the hats will represent the predictions that we're making. And what are we doing today? Well, today we'll try to learn the best model from some class to predict y hat. So I just introduced a few new things here. F here, this is our model class. F. F takes an example, X, right? And it takes the parameters of the model. So W are parameters. And we choose a model class, F, that's a function that maps from examples, takes in parameters, makes a prediction, y hat, and then we're trying to learn the parameters that give us the best possible model. So how do we do that? Well, we need three things. One thing we need is we need to know what model class F are we working with. The second thing is we need what we'll call a loss criterion. We need to know what we mean by best. Well, how will we know when we've picked parameters that are good? So we need what we'll call a loss criterion. We'll write that with this script L subscript script D to represent the data. So read this as a function, script L. I'm going to write D just to remember that the function kind of carries the training data with it, D, and it's a function of the parameters W. And it returns a real that represents how good the model is for the parameters W that we pick. And then 3, we want to choose parameters, which we'll write as W star. These will be the parameters that we like. That's what the star will indicate. To minimize this loss function. Right, so lower will be better. And the thing that's going to be really neat, I hope we'll see by the end of our session today, is that we'll be seeing linear algebra and calculus coming together in a really beautiful way to understand how to solve this problem. Let me pause, though, to check if there are any clarification questions about what we've done so far. Also, of course, you can be using the chat, and we've got lots of TAs and co-instructors here to help on chat. But if you do have any clarification questions, also notational questions, this is a good time to ask, because you should definitely understand everything I've written so far. Go ahead and raise your hand or chat if you have questions. Yep, X and W are vectors, Y is a scalar. Dimensions of W, I haven't specified that yet, but I'm about to. And it's not a 0 next to the L. Let me try to rewrite it. It's a D. And maybe I'm just trying to be too clever. It's just a D representing the data. So it's basically saying that the function is defined both on the data and on the parameters. We choose to write the data as a subscript just for notational reasons, because we really just want to think about the loss as a function of W, but it does actually depend on the data as well. What does the loss represent? The loss represents the goodness of the fit, and I'll tell you more about that in a second. And then a class, I don't think we've talked about classes yet, but when we talk about classification rather than regression, we will talk about classes. Okay. All right, great. Feel free to keep asking other questions in chat. I'm sure other people will answer them. So now let's go through these 1, 2, and a model class is a function class. Yeah, and maybe others can also type more. So for our model class, this will make that a little bit more clear, actually. We're going to use what we'll call linear models, and that's why this will be linear regression. So we'll make a hypothesis is that there exists a good linear function of the input. Now remember, our input is it's always a column vector, but if I want, I can write it as a row vector as long as I write the transpose above it. That's the feature vector, that's the input, that's what we're making the prediction on the basis of. What does it mean for it to be a linear model? It means that the function f, which again takes my feature vector x and my parameters w, which is also a vector, oops. Looks like this. So I take my parameters. How many parameters do I have here? So you can see here that my parameters, I've got d plus 1 of them. Remember, my feature vector is dimension d. I've got d plus 1 because I also have this term, w0, which we think about as a bias term. Okay, so my parameters are w1 is the amount by which I multiply feature 1, w2 the amount by which I multiply feature 2, etc. This is a linear model class because there are no interactions between the x's. That's what makes it linear. And just to note that it's going to be convenient to hide, or if you like, forget about the bias term. What I mean by that is that I'm going to be willing just to write the following. I'm going to be willing just to write this all as an inner product between the weight vector and the x vector. Okay, so what happened to the bias term? Well, I can handle that just by bringing a 1 into my x vector. So if I'm willing to pretend that my features always include a 1 in the first position, then I can handle my bias term conveniently by by pretending that there's an extra dimension to the feature space. So that now the first parameter or weight w will represent the bias term. So we're not going to worry about the bias term going forward. We'll just always be working with this object as a linear model class. And we'll be looking to find these parameters, so I'm also calling them weights or coefficients w, that give us a good fit from that model class. Any questions about this? Any clarifications? X's and W's are column vectors. So we're always using column vectors in this class. So remember, when I take the transpose, then I'm getting the inner product by taking the transpose of the first vector and writing down the second column vector. Okay, so that's one. We'll be working with linear models. Hopefully that's clear. And then two, what is our loss criterion? We need a loss criterion. Okay, so this is this function of the parameters W. And what we'll do for our first look at linear regression is we'll take the loss function as 1/2 of the sum of the square of the predictive error. Okay, so remember my training data includes n examples. The y's are the actual target values in the data. The y-hats are my prediction. Just take the sum of the square of the difference between your prediction and the true value. And if you want to have a picture in mind, generally you can be thinking about this in one dimension. I have a hard time thinking in more than one dimension, so I would encourage you to think about this in one dimension. And generally in one dimension, if those are my points, and that's my linear model that I've fit to the data, then what we're doing is we're thinking about those distances. The y-hats live on the line that I fit, and those distances are the errors that we square and add up. And those things go by the name residual. Residuals are the mistakes that you're making on the training data. If the residual is positive, the true point lies above your prediction. If the residual is negative, the true point lies below the prediction. Okay, so this is the basic approach that we'll be taking. This is giving us this what is now called least squares regression. And next class, we'll be talking about how this is really a mathematical convenience. Really, the criterion you take should be something that depends on your problem, but this will turn out to be mathematically very useful for us. And why is that? Well, the third step is we need to know how to optimize and find a W star that minimizes the loss on my training data. Okay, so we're looking for a W star that is this is like an argument that minimizes this function. That's what we're looking for. W star that minimizes our loss function. And you might have two different pictures in mind of this. Right? The world could be nice. Oops, this is W. The world could be nice and friendly, and your loss function might be beautifully convex. This is a convex function as a function of the parameters W, here just in one dimension. Again, generally, this is all multidimensional. Thinking in one dimension should get you a long way. Or the world might look much more complicated. And here's my loss function. Here are my parameters. So this here is a convex problem. And that's useful. If we have a convex problem, then what we can do is we can find the good W's, the W stars, by looking for the point at which the derivative of the loss with regard to the W is 0. That's the first order optimality condition. So that's one thing we could do. One thing we could do, 3A, is we could take an analytical approach. use first order optimality conditions, which we'll talk about a little bit more in a second. You also need to be checking second order optimality conditions. If you can do this, and if you can solve this algebraically, that's great, and that will give you a solution to your training problem. But if the problem is much more messy, for example, if your model class is not linear, but is, let's say, a neural network, then you're going to have a loss function that's all kinds of crazy. And there won't be an analytical solution to the global minimum. And what you would typically do instead is use gradient methods. So these are methods that are going to try to walk through that space and try to find a good minimum, but won't necessarily be guaranteed to solve the problem correctly. And today, we're going to be focused on analytical approaches. Because the nice thing is that by working with the squared residual as the loss function, we'll be able to get an analytical solution. The problem will turn out to be beautifully convex. I think this is, again, a good point to pause to see if anybody has any questions about what I've just said. Either chat or raise your hands. Yep, second order optimality is checking essentially that the second derivative is positive. Talk more about that in a second. Okay, great. Yeah, so first order conditions and second order conditions. First order optimality conditions and second order. And these are things from calculus to find the optimal points of functions. Right, if you had, I don't know what you mean by a simple non-convex function, but the answer is maybe yes, but let's take that one offline. Maybe. Okay, now, how are we going to do this? I just want to give you a few reminders of some things, and then we'll do a little bit more math, and then we'll take a break. Okay, so how are we going to do this? Let me recall a few things, first of all. Suppose I have a function which goes from d dimensions to 1 dimension. Then one thing I want you to remember, hopefully you've seen before, is the gradient vector of that function. What's the gradient vector? It's the vector where the components of the vector are given by the partial derivatives with regard to the parameters of the function. So this is the gradient vector. That symbol is a nabla, if you're wondering. And the thing you need to know is that this points in direction of steepest ascent. And that will be useful when we're doing gradient following methods. This is a gradient vector. It points uphill. Think about it that way. A gradient method will work if, this is on the chat, a gradient method will work if the problem is convex, but in general, it's not guaranteed to work. And then I just want to give you a couple of things to know about. First of all, remember that these are scalars. If I have scalars, I can reverse the order and get the same scalar. So the derivative of this scalar with regard to excuse me, should be writing this using the gradient symbol. Actually, we are happy. Let me just tell you that we are also happy to write this as two things are equivalent, but just to be consistent, let me use the same notation. So this is one thing that I want you to know, that, and this is a linear function. So the gradient vector will just take the coefficients on the parameters that you're taking the derivative with respect to. And then the second thing I want you to know, because we're gonna see it in a second, is that, oops. If you have a function like this, then the gradient vector takes this structure. And if you're wondering where these things are coming from, the first one you probably have some intuition for. Second one may appear somewhat mysterious. You can look at things like the Matrix cookbook. Which you can Google for, and has all kinds of identities about calculus in regard to linear algebra. And the one that I just want to remind you about is that the transpose of a product of matrices can be equivalently written like that, right? And so our roadmap now is that we are going to be thinking about this nicely convex loss function. And we're going to be, first of all, working with the first order optimality conditions and quickly checking the second order optimality conditions. And those will give us a solution to the linear regression training problem. And as we do that, we're going to appeal to identity 1 and identity 2 at some point. So I think this is probably a good moment to take a short break. So let's just take a couple of minutes. We're gonna activate the breakout rooms in case you want to go find people to hang out with. You can also just hang out here, of course. We'll take a couple of minutes and then we'll get going again. Reminder, we've created like 2 sets of rooms. The second set of rooms you can use to go say hi to people you know if you like to.
I have a quick question. If that's all right.
Sure, go for it. Yep.
Earlier we said that we call it a linear regression if there are no interactions between the x terms. I was curious if we had like a kernel that was transforming the x's, maybe like using trig functions or something, and then we have our weights on the results of that kernelized input, would we consider that a linear function still, or is that no longer linear?
Yeah, good question, Benjamin. We would still consider that to be linear. It will be linear in a new feature space, and I'm going to talk about that at the end of our session, actually.
Thanks.
Yep. I just saw the chat. Some of you want to still see the notes. Let me keep sharing. I'll also be posting the notes after class, so you'll be able to read my scribbles at your leisure.
There was a minor correction that someone pointed out where I think there was a W star in the loss if you go up a little bit.
Yeah, right here.
Yeah. It should be an equals.
I guess it would be equals if there's
It was a
a
unique solution.
if there's a unique solution. There's not always going to be a unique solution, so we might prefer
This is
to write
still
it this way.
general, but we hadn't made this linear regression yet. Good point. Fair.
Yeah. Yeah, but it's a good notational point. So the reason I am writing is a member of here is there could be multiple solutions. Turns out there will only be one solution for what we're doing. Great.
David, should I clear the other two large text things, or
Sure. Yeah.
just so we have that on our radar?
Yep. Okay. Any other clarification questions for any of you before we dive back in? Great. All right. So how are we going to solve this? So remember that the loss function is this guy. So I'm writing y hat now as the inner product between the coefficients w and the feature vector xi, adding up over all of my examples. And now what we want to do is we first of all want to take the partial derivative of this and set that to 0 and try to solve. Now, first of all, that will be additive, so we can distribute the derivative over the summation, and then we're also going to appeal to the chain rule. So appealing to the chain rule, right? I've got 2 times this term canceling out with the half, and then I need to take the derivative of this term with regard to w, which is just x of I as per equation 1 that I reminded you of earlier. So this is chain rule and equation 1 from the previous page. And I need a minus, because when I take the derivative of the chain rule, I get a negation as well. If you wanted to simplify this, of course, you could write this out as this. Okay. It's always good, by the way, to check dimensions whenever you're doing any linear algebra. So here, the gradient vector should have dimension D, because that's the dimension of our feature space. Remembering we're not worrying about the +1 because of the bias term. And indeed, this is a scalar multiplied by something of dimension D. This is a scalar multiplied by something of dimension D. So it has the right dimensions. So that's good. And then what we would do is then we would set to equal 0 and solve. And then we have to check what I've been calling the second order optimality conditions. Right, there should be a negation there. Okay, remember everything I'm underlining are vectors. I see there's some chat about that. And at some point we will probably stop underlining, but I'm doing it for now. And when you read the textbook, you'll see things in bold. Okay, but what we actually want to do is we want to solve this a little bit more elegantly. So a second look using linear algebra. And now we're going to try to do exactly what I just did, but linear algebraically. And to do this, we'll introduce what is called the design matrix, which is just a fancy word for all of the training data. We'll write it as capital X. I'm writing matrices using capitals. I'm not underlining them. This is going to be an n by d an examples D dimensions matrix. What does it look like? Each row in the matrix is one of my examples. So the top row is example 1, which I need to write with this transpose because remember, my examples are column vectors. So the first row is example 1. And if you want to write that out in full, it's going to look like this. So that's my design matrix. It's just all my training data. If you're used to thinking about data frames, if you do applied machine learning, each row is an example, just like the way we normally would think about data frames. And then also write Y to stack together all of my target values in my training data. Okay, so once I've done that, it's very convenient because I can write my loss function, my loss criterion L, linear algebraically like this. Let me explain why. So again, this Y contains the target values for each of my examples. So the first entry is the target value for example 1. And remember, what is going to be the result of multiplying this matrix by the column weight vector? Well, the first entry, the first entry in the resulting column vector will be exactly taking row 1 and multiplying it out by the parameters, which is exactly the prediction for example 1. So hopefully you can see that by taking my design matrix and multiplying to the right by my parameter vector, I will get the Y hat vector. So then this is taking the difference between the Y's. So this is my Y hat vector, the Y hats. And then I'm just taking the inner product between those two things by transposing, which is giving me 1/2 of the sum squared of the difference between the Y's. So it's the linear algebraic expression for what we've been talking about. And I'm trying not to underline my capital X's. Thank you. All right, so let's just go ahead and expand this. This is when you just kind of have to, I guess, what we would say is go with the Zen. Kind of, it's almost like pretend that these things are just normal scalars now when you multiply out. There's a way I like to think about it. So I'm just going to breeze through this. First term of each. Right. And
hey, David, there's just been a lot of questions in the chat related to like incorporating the bias term. Just repeat. Maybe it's worth clarifying for everyone where the bias is in this equation.
Yeah, good. Right. So first of all, generally it's okay just to forget about the bias term if it's confusing you. But generally we do want a bias term in our linear models because they'll give us an offset from 0, if you think about a very, very simple picture. And the way that we'll handle the bias term is just by essentially introducing into every example a feature whose value will always be 1. If I have a feature whose value is always 1, then I can multiply that 1 by my parameter, my corresponding parameter, and that will give me my bias. So you should think, if you want, that there's an extra column in this design matrix of 1s all the way to the left. And we always add that column of 1s. I'm not talking about it explicitly because you can just pretend that it's an actual feature in the data, and then it will give you a bias. So hopefully that helps. And yes, final term should be a plus. Thank you. Good. All right, I think we're typo free. I want to point out now that this is a scalar. It may not be immediately obvious. You have to check the dimensions, but indeed, if we check the dimensions, this is, let's see, let's just do it because we're doing it for the first time. 1 by n is y transpose. X is what? N by d. And w is d by 1. So you can see that you get a scalar. Though, so because it's a scalar, you can take the transpose. The transpose of a scalar is the same thing. So what I can do is I can take the transpose of this, and then actually it's equal to this. If you think about it, you get the same thing. So then what I can do is I can simplify everything and just write all of this. I'm actually going to also, let me at the same time simplify this transpose. Okay. So this is using the fact that the transpose of a scalar is a scalar. And now what I'm ready to do is I'm ready to take the derivative of this. And when I take the derivative of this, because it's going to give me my gradient vector, this term doesn't depend on y, so it goes away. This term is just going to be this x transpose y times a half minus 2, which is just minus 1. Using rule 1 from the previous slide. And this term has the structure of rule 2 on the previous slide. So it's okay. So here we used 1 and 2 from the previous slide. And now what I can do is I can set this to 0 and solve. And if I set that to 0 and solve, then actually, first of all, recognizing that this, let me actually write one more little line out. First of all, recognizing that this is the same as this, if you use your transpose rule. And I lost a half here. So now I've got plus that. And now I can set that to 0 and solve. So set that to 0 and solve. What do I have? I have trying not to write those bars underneath the x's. This. Now we can take the inverse of x transpose x and I get this expression. Now, this is an algebraic answer. We haven't checked the second order conditions yet. Also probably looks somewhat mysterious. I want to make one comment about this, which is that we took an inverse. Now, you can only take inverses if matrices are non-singular or full rank. And for that to be okay, we need the design matrix X to have full column rank. Okay. Next thing I'm going to say is out of scope, but if you're curious why the full column rank of X lets that be invertible, you can argue relatively easily that it makes X transpose X into a positive definite matrix, and positive definite matrices have inverses. That's kind of out of scope, I think. I don't think it's even in the problem set. What I want to emphasize is this interpretation. So I said full column rank for this solution to be valid so that we can invert this X transpose X matrix. What does that mean from a machine learning perspective? Well, the interpretation of it, remember what X was? Remember X was full column rank means that the features are not collinear with each other. This is about the features not being collinear. So one feature should not just be, for example, a scalar multiplier of another feature. And we'll have an example of that in a comprehension check towards the end of class. Features should not be able to be represented as combinations of other features. This is often thought about in machine learning as a redundant encoding problem. Let me try again to write that. You shouldn't be carrying the same concepts in your features in multiple ways. If you are, then you're not going to be able to take the inverse. And if you almost have a problem, you'll get numerical complications in trying to take the inverse. Right, so it's one thing just to be watching out for, and you can see it coming through in the mathematics. What I do want to do is we didn't do, this was just the first order optimality condition. We didn't yet take the second order optimality. So I do want to just quickly write that down. So let's take the second order derivative of our loss function. And we have the first order derivative here. So I just take the derivative of this again. This term doesn't depend on W. This term does. So it's just X transpose X. And this is positive definite for the same reason I described before, as long as the matrix has full column rank, and positive definite for multivariable calculus is sufficient to get this convexity. And that tells us that what might have only been a local minimum is actually a global minimum. And if you want just some intuition for why a positive second derivative, in this case, because we're using matrices, a positive definite Hessian, this is a Hessian matrix, think about one dimension. In one dimension, we set the gradient to 0, we solve for this point. Take the second derivative, well, notice the gradients are increasing from left to right. So the second derivative is positive everywhere. So positivity of the second derivative gives you this convex shape, and the same intuition carries forward to multivariable. And yeah, positive definite, just as a reminder, this is kind of something that is in the section 0 review, but just as a reminder, is that matrix A has that property when pre and post multiplied by Z transpose Z. It's strictly greater than 0 for all non-zero Z. That's positive definite. Very powerful property, tells you something about the solution of the algebraic problem to your optimization problem. Let me pause, take a few questions, then I want to make a few comments, and then I want to give you a short comprehension exercise before we wrap up class. How do you watch redundantly encoded features? Good question. You'll typically be wanting to do some actual linear algebraic or computational work to try to find them in your data. And there are also things you can do to try to avoid the problem that we've just described. One is that gradient descent is actually much less vulnerable to this collinearity problem than this matrix inverse approach that we just described. Another thing you can do is to perturb the features a little bit. We're going to talk about regularization later in the semester. That also helps a lot as well. This redundant encoding is just kind of a word used in machine learning. For the idea, for example, the gender, you could remove the gender feature from your data, but still be able to recreate the concept of gender from the other features. That's why we would say that gender is redundantly encoded by other features in the data. Yeah, and when we're doing multivariable calculus, unfortunately, the second derivatives do become a matrix. You have to think about the Hessian. I'm not going to spend time going over that, but if you read about the Hessian matrix, Hessian, it's a matrix of the second derivatives, and that matrix has to have the right structure. Okay, let me make 3 quick remarks, and then we'll do a comprehension check, and then we'll break. So note 1, I'm not going to dwell on this, but there is a statistical interpretation of what we've just done, where you can actually think statistically about what this estimate W star, you can think about W star as the estimate of the parameters of the model. And remember, we said that it's this, it's given by this. And if you want to read about this, I'm just going to leave it as a teaser. It's out of scope for our class, I believe. But this is what's known as a blue estimator. It's the best linear, unbiased estimator for the problem. Out of scope, but if you want to read more about that, you can. So this is, we'll just say it's a good statistical estimator. And then note 2 I want to make is that I think in the interest of time, the next note I want to make is not to talk about the geometry of this, but to mention what I was asked about in the break by Benjamin, which is, okay, this seems neat. We've just been able to write down a linear algebraic formula for the solution to an optimization problem, but is insisting on linear restrictive. Seems like it might be restrictive. And I said linear means there's like no interactions between things. Well, the answer is no, because you can bring in what we'll think about as basis regression. So let me give you the basic idea here. The idea is to take our feature vector x and map it to a new vector given by phi we're going to map this through this basis function phi and think about it as generating for you a whole new description of your example. And then once we've done this, so now essentially you can work with this new form of your example. You don't work with x anymore. You work with this mapping of x. Once you've done this, then you can still be linear in that new space. So you essentially expand the feature space out to a higher dimension. And I think I don't have the time to walk through examples of that, but just to mention. Yeah, go ahead.
I was going to say that you'll have plenty of opportunity to play with that in question 4 of your homework. So at this point, you should have everything to work on your homework problems due in a week.
And I'll also write a little bit more before I post these notes so you see a little bit more about this. But just to mention, there are lots of ways to make this mapping. One simple thing is you might take your features and take the quadratic interaction of all of them. So take feature 1 and multiply it by feature 2. Take feature 1 and multiply it by feature 3. And those become your new features. And then you're linear in that new feature space. And that can be very powerful. So what I want to do is do a quick concept check with you all. Let me just walk you through this, then we'll go into breakout rooms, and then I'll tell you what you should have thought the answer was. Question 1, there are 3 examples of data sets, just one-dimensional x versus y. There are 3 lines for each one, and we ask you which line is the best fit from a least squared viewpoint. Question 2 is asking you how you might detect issues with the fit. Is it that there's a pattern in the residuals, that there are one or more large residuals, or that there's an extreme x value? You may be unsure. Question 3 is describing this, and maybe see if I can make that a little bit bigger, is describing this very simple model of how far people can jump. Okay, so there's W0 plus W1 times the height of the person plus W2 times the leg length of the person. And that's supposed to be a model of how far people can jump. And it says for the jump model on different runs, now we haven't talked about gradient descent, but just kind of picture a gradient following procedure. For different runs of a stochastic variant on that, we obtain one time weight 1 is positive, weight 2 is negative. One time weight 1 is negative, weight 2 is positive, and a third time weight 1 and weight 2 are positive, all with the same accuracy. Which of the following could help to explain this? And what I'm going to do is I'm going to post this to the chat. So hopefully that Google form works. Can you check it works? And then what we'll do oops, they're already moving to breakout rooms. Okay, hopefully they got the link. Oh, but I can send the link to everybody. Okay, loads of you still here. You should have an invite to breakout rooms. Did it happen?
Not yet.
Interesting. Oh no, some of you moved to breakout rooms. Oh no. I wonder why that would be. It's surprising if you're all using an outdated breakout room. Rats. Yes, okay, what to do? Maybe I'll have you try to self-select. Hang on. I thought that was going to work. Yeah, we're almost out of time. So I think what I'll have to do instead is just walk you through this, and we'll have to do a better stress test on this. Apologies. So then rather than sending you to breakout, given that they seem to not be working, let me just do a very quick walkthrough of the concept check. So first of all, we ask which of these 3 lines is the best fit to this data. And if you think about it, hopefully you would agree that 2 is going to minimize the least squared error for this fit. Here's another example where there's a small number of points up here and 1 point all the way down here. Again, if you think about it, I think probably this doesn't look very good. Then you might be trying to decide whether this fit minimizes the squared error or this fit does. And the way I want you to think about it is, suppose this point is quite a long way away from these points, and suppose there are not very many points here, and they're quite close together in this dimension, then this would end up being the best fit. And then the third example is data that looks like this. And if you're minimizing least squared, and I gave you the choice of 1, 2, and 3, I think you would all probably pretty quickly say this is the right thing to do, number 2. So that was the first comprehension check, and apologies I'm having to walk you through it like this. The breakouts didn't work, and we'll fix that for next class. Now, I think a little bit more subtly, we ask you how you might detect the issues with the fit. Choices are, is there some kind of pattern with the residuals? Are there 1 or more large residuals, or is there an extreme X value? So pattern, 1 or more large or extreme X. So for this one, I wonder if one of you wanted to raise your hand and say which of those 3 explanations would you think would be a good thing to answer to that question. Akash, please.
For the graph with what looks like to be a parabolic curve, it might be better to see if there's a pattern in the residuals, because it looks like there's a nonlinear trend.
Yeah, and indeed, that's exactly right, Akash. And notice that if I went with fit 2, these points have negative residual, they're below the line. These ones have positive residual, they're above the line. And these ones have negative residual, they're below the line. So I have this negative, positive, negative structure to the residuals, which suggests that I've missed something structural about my data. And in this case, for example, I would want to use a basis expansion and maybe introduce the polynomial basis and take the square of points to be able to better represent this. So then in this example here, what would we say? Would we say a pattern of residuals, or 1 point with a big residual, or 1 point with a very different X than the rest? Joshua?
It's that there's an extreme X value.
Yeah, here's our extreme X value. And then this one, extreme X, pattern of residuals, and suppose we go with fit 2, or like a small number of points, maybe 1 point with a very big residual, it's the 1 point with the big residual. I think you all see that. And then lastly, on this question, where we have this linear model of height and leg length to predict jump distance, and the answers are, is it, and we see these like 3 very different fits, either positive on height, negative on length, negative on height, positive on length, or positive on both. Option 1, is it the gradient descent is a poor method of optimizing? Option 2, is it collinearity between height and leg length? Option 3, is it height doesn't predict jump distance well at all, but leg length does? What do you think? Does somebody want to offer an answer to this? Charumati, please.
Yeah, so I thought it was collinearity between height and leg length because since they're related, if one changes, then the other is likely to change as well.
And you are exactly right. And notice that collinearity doesn't mean in this case that we didn't get a good fit. It just meant we got different fits. They all fit well, but we got different fits each time we tried to solve the problem. Good. Okay, we're out of time. Apologies for the breakout room problem. We'll make sure that's fixed by the next time we get together. And just as a reminder that your first problem set is out. As Finale said, you should now be equipped to be able to make progress on that. And it's due on Thursday of next week. But there are also 2 late days per assignment if you choose to take a late day. There are office hours continuing all week. Finale, I think you're having yours today, aren't you?
Tuesdays.
Tuesdays. And then I'm having mine for this week only tomorrow afternoon. And we'd love to chat with as many of you as want to show up. We understand there have been some problems with Collaborate, maybe some technical problems. We're going to keep testing it this week. If it seems like Collaborate is not working for office hours effectively, we'll move to Zoom. And we may put out a poll to ask for your feedback on that as well. I am going to hang out here in case any of you have any things you wanted to ask about before we break. Max, please.
Yeah, I had a quick question from when you were talking about the basis regression. Oh, okay. I'll join you in the room.
No, this is fine. I just opened the rooms in case anybody wants to join, in case anybody wants to chat. Oh no, and now everybody's going automatically to rooms. What? How can that be? That's so strange. Okay, let's wait for Max to get back.
Hi, sorry.
No, that's so funny. So that time apparently automatic assignment worked when I didn't intend it to work. I just opened the room so you could all hang out and chat with each other if you wanted to. Max, please.
So I had a question from when you were doing the basis regression, which is that when you drew the output of the function phi, it looked like in the vector you had phi sub 1 of x and phi sub 2 of x. And I was confused about whether or not there are multiple phi functions that are indexed with different subscripts, or whether there's one phi.
Yeah, that's a good question. It's that there's one, I mean, you can think about it either way, but I would propose you think about it as this one function, and the function takes something in dimension D and returns something in dimension M.
Okay.
And then and then when I write, and we'll typically write that in bold, it's a vector valued function. And then when I write, and actually now I'm trying to think whether I should have written these guys up here underlined or not inside here. I think probably that would be clearer. When I write this, what I mean is the first entry of the vector generated by the basis mapping.
I see.
Does that make sense now?
Yeah, but it has a dependency on all of x, so that's why it's a function of x.
Right.
Exactly.
Okay. And so that could be, like you were saying, M could be way bigger than D if you want to put in, the quadratic terms and some interaction terms and some other stuff like that, right? Is that why?
Exactly right.
Okay. Okay, great. Thank you so much. That makes sense.
Yeah, good. Justine?
Yeah, sorry, could you just explain again the answer to the last question of your poll with the gradient descent method?
Yes. I think I probably don't need to pull up the example. Let me just speak to that. Stop the sharing. Yes, so the point there was that imagine that height is correlated in the data with leg length, right? Typically taller people will tend to have longer legs as well. And so if you further imagine that the height of somebody, and therefore also the leg length of somebody, affects how far they can jump, then if I want to build a predictive model of how far somebody can jump, I could either pay attention to height, or I can pay attention to leg length, or I can pay attention to a mixture of both. And notice that I can even, let's say, overweight height, so have that be a positive coefficient, if I'm willing to subtract out some of the weight on leg length. Okay, so it's getting at this collinearity between the two features.
Okay, thank you.
Yeah, sure. Sahaj?
Hi, yeah. I had a question about the, so I think you said that the criteria you need for a matrix to have an inverse is that you need it to be greater than 0 in that definition with the Z. Is it okay if it's greater than or equal to 0, or does it have to be greater than 0?
Yeah, so I was referring to positive definite, which is strictly greater than 0. Positive semi-definite is weakly greater than 0. Positive semi-definite is sufficient for invertibility. It turns out here we will get positive definite, which is why I expressed it that way. But positive semi-definite is also enough.
So I was trying to see what the proof would be to get it to positive definite, but I could only get it to positive semi-definite, where if you just square the elements of the matrix, it's greater than 0. Well, it's greater than or equal to 0, but I thought that there could be a possibility that it would also be just 0.
Yeah. So you probably got to the point where you had the kind of the inner product between Z transpose A in itself is weakly greater than 0, and then the missing piece is to argue that the inner product that Z transpose A is strictly greater than 0 because A has full column rank. And so you cannot get 0 for any non-zero Z. And so if you add that, what you've already argued, then you get the positive definite.
I see.
And another way to maybe think about it is if you think about positive definite as having full rank, then you can, you know that you're, if D is greater, sorry, N is greater than D, and you're creating the D by D matrix by multiplying rank 1 combinations of N together. Now you have to assume that all the X's are not all on top of each other. That's going to be the key assumption that you have to make. But that's maybe an intuition, right? There's the proof that you can do, but just sometimes it helps to know kind of why this whole thing should be possible in the first place.
Yeah, that makes sense. Thank you. Thank you.
Benjamin.
Hi, yeah. So I'm just curious, maybe this is coming up. If you're doing a project on real world data, and maybe it's categorical, and you took 2 observations that happen to have the same measurements, then your design matrix is going to have 2 copies of the same row and be singular. And you mentioned that was it perturbation is one possible solution, and that gradient descent is robust against this?
Yeah, so two different things. So you know, having collinearity is what you might, if you want to use a mathematical word, is non-generic. You wouldn't typically expect that. And so if you just slightly shake like the two feature columns, then you will no longer be exactly collinear. And then in principle, you could now be able to invert that X transpose X matrix. Now, numerically, it's still going to be probably pretty unstable. So I don't really recommend that as a way out of this. It's just kind of a mathematical observation. I think, and then I made a separate point, which is that gradient descent, you know, it doesn't really care if there's more than one direction to walk in. Kind of okay, it'll walk in one of the directions. So gradient descent just tends to be more robust in that sense to this collinearity problem. Is that?
Thanks.
Yep. Awesome. Any other questions from any of you?
Yes, I have a question. I'm still curious about what phi 1x is.
What phi 1x is? Just think about it as a scalar. It's a scalar that represents a new feature that you've created. So if you want to think about it, just a very simple version of this, phi 1x could be, suppose x is just a scalar, okay? So suppose your initial feature space is just a scalar, just a number. Then phi 1x you might define to be x squared. Phi 2x you might define to be x cubed. Phi 4x you could define to be the sine of x. So you can basically create whatever new features you want as a function of the original feature.
So the dimension of phi 1x is the sum of x?
Phi 1x is always going to be a scalar because it's one of the entries in the, maybe I'll show my screen again. Hang on. So let's just be very concrete. Suppose that x is a real, and suppose that phi of x is defined as 1x, x squared, x cubed. Okay, so this is an example where my basis mapping is from R to R to the 4. And phi, sorry, I don't know why I've started writing bold phi. I mean, not write bold phi. And now phi 1x is x, phi 2x is x squared. So notice these are always scalars. We have to have scalars inside here. Does that explain things now?
Yeah, I understand. It makes sense.
Great. Okay. Glad to hear.
Thanks. Goodbye.
You're welcome. Bye. Michelle, do you have anything? No, just hanging out, I think.
Okay.
Okay.
Good.
Good. Oh, and I realized I forgot to stop the recording.